Bocconi math courses require you to understand the use of mathematical notation and terminology. This will come up in exercises where they use notation to indicate certain things about sets and functions, for example, that you have to understand to be able to answer the question. And also in open answers, they often ask definitions and theorems, where usually you have to write everything formally using mathematical notation. So we'll start with the different types of numbers. The ones that are highlighted in yellow are the ones that are most frequently seen. First, we have the real numbers, so these are called R. This represents everything from minus to plus infinity. Notice how I use parentheses versus here I have brackets. The parentheses implies that the two extremes are not included, so the minus and plus infinity are not treated as actual possibilities, versus if you have the brackets like over here, then they are going to be considered as actual possibilities. So we mainly use the extended real numbers when we're dealing with limits, because with limits often you have x tending to minus infinity or x tending to plus infinity, so we're treating those as actual values essentially for x. And for both, we can say that they're going to be dense and continuous. So dense implies that if you take any two real numbers, you're always going to find at least one real number in between. Specifically, you're going to have infinitely many. And continuous implies that in addition to that, we also have that there's no gaps in between any two real numbers. So you can see this visually, it's just everything on the number line. There's no spaces essentially between any 2 points. Then we have R squared or R2. So this is simply when you have all real numbers for both x and for y. So we just have two variables, each which can take on any value. Visually, this would be everything on a Cartesian plane. So here I have just everything shaded, versus before we had everything on the number line. So these are little things that you should pay attention to in exercises if they mention that a set is a subset of R or a subset of R2, because that's going to affect how you represent it graphically. Then we have the integers, which are all the whole numbers, including also the negatives. So these are some examples here. The natural numbers, which are specifically the positive integers, and positive does include 0, so this might vary depending on other courses that you might have taken, but at Bocconi they consider positive to include 0, and strictly positive would be everything greater than 0. So natural numbers, we can say that they're positive integers. If we wanted specifically the strictly positive natural numbers, that would be from 1 onwards, but they would have to specifically say that they want the strictly positive ones. Then the rational numbers are the numbers that can be written as fractions of two integers. And the irrational numbers are the ones that can't. So the irrational numbers are everything in R excluding the rationals, so R excluding Q. The slash means excluding. You could also call them P, but this is not frequently used. Both types, so rationals and irrationals, are going to be dense but not continuous. So this is different from real numbers, which are dense and continuous. So since they're dense, that still means that between any two rationals, you have at least one rational, and between any two irrationals, you have at least one irrational. But because they're not continuous, that means that you are going to have gaps in between them. So if you were to represent them on a number line, it wouldn't be, you wouldn't have everything connected like we had in this case. And we can also say that if we take any two real numbers, between them we're always going to have at least one rational and at least one irrational number. Now we have sets, which are collections of x values, or in other cases x and y values, depending on the situation. First, we have the concept of the universe, which is just all of the possible x values that can be considered. The empty set just represents no possible values, so it's like saying nothing. And the usual notation for a set is A. You can also use other capital letters like B, for example, but usually they're going to use A. When we're dealing with functions, often that's going to represent the domain. So the domain is a set of inputs for a function. And if we're talking about a one-variable function, it would be the possible x values. If it's a two-variable function, it would be the possible x and y values. The complement is simply the opposite, so everything that is not in the set. So in the example of the function, it would be everything outside the domain. And the image or the range of the function, they can call it IMF, so image of the function, or f of a, where again a is the domain. This represents all of the set of actual possible outputs for the function. So if we're dealing with the one variable function, it represents the y values. This is different from the codomain, so later we'll see that if we are dealing with the function, the codomain range don't necessarily have to coincide. We can say that the range is a subset of the codomain. It's restricted by the codomain. Then we have subsets, so we have a strict subset. It's almost like having a smaller than sign. in the sense that when we say that a set is a strict subset of another one, like for example, if A is a strict subset of R, it means that A is smaller than R, so it's inside R and it's also smaller. It's not equal to it. Versus if we have the classic subset, which is more common, this implies that if A is a subset of R, it's inside R, which means it could also be potentially equal to R. So it's kind of like having a smaller equal sign. And if we have the two sets are equal, so A equals B, we can say that A is a subset of B and B is a subset of A. So again, this is actually very similar to smaller equals to signs. We can say that if X is smaller or equal to Y and X is bigger or equal to Y, it's equivalent to saying that X equals Y. So it's the same concept. When I use a double arrow, this means if and only if, which we'll talk about later. So this implies that A equals B is a necessary and sufficient condition for these two to hold, and also other way around. Then we have excluding, which we saw before when we talked about the irrational numbers. They were written as R excluding Q. So it was R excluding the rational numbers. And then we have union and intersection, which you're probably familiar with. Union is like saying or, and intersection is like saying and. There are a few more symbols that are used in various contexts. The first is the such that symbol. This will mainly be used with functions later on. Then we have belongs to versus does not belong to. So if, for example, we're trying to say that X belongs to the domain of the function, we can write it like this. Or if X doesn't belong to the domain, we can either say X doesn't belong to A, so it's not an element of, does not belong to A. Or we can say that X is in the complement. The complement is everything else outside A. Then we have the next two that are used often in definitions, and this I've noticed that they often try to mix you up in the multiple choice. If they ask you a definition that uses one or both of these symbols, they often mix them up. The first one is the upside down A, which implies for every, and then the backwards E implies there exists. Specifically, it means at least one. So if we have an equation that has at least one solution, we can say that there exists a solution without specifying how many. If we do want to specify that we have exactly one solution, then we can put an exclamation mark, but this is not going to be used very often. Then we have X, which of course represents a one variable number. If we write X0 or X with a hat, or there's also some other little variations, this represents a specific value of X. Versus here, it's just a generic value. Here, it's a specific value. And if we put a line underneath, it becomes a vector, or you can also make it bold. In exercises, since of course they're going to be typed, they tend to make it bold, just because by computer it's easy to do. But in lecture notes, if it's handwritten, usually professors will put a line underneath. So from this point on, I'm just going to put a line underneath just because it's easier when you're writing it by hand. And a vector just means you have more than one variable. So if, for example, the x vector is equal to 1, 2, which you can write like this, or you can write using brackets. Since it's a vector, this implies that this is your first variable and this is your second. So this is x1 and this is x2, or you can call them x and y. You could also have more than two variables. Then we have distance, so usually they write dist of x comma y, or d of x comma y. You can also use this symbol, which is a norm. In that case, you have to write it as the norm of x minus y. And the norm, if we take the norm of x, it represents the distance between the null vector and the x vector, so from the origin to the x vector. So here we'd be taking the distance between x minus y and the null vector, if you look at it like that. But it's easier to just think of it as if you have subtraction here, notice how it's subtraction, not addition, then it's like saying the distance between x and y. Then we have a few examples. So these last three are going to be intervals. Intervals are sets in R, so specifically R, not R2 or higher, so you just have one variable, that have no gaps, so they're going to be continuous. And you can have, for example, 1 and 2, the two extremes, excluded. So this is like saying that x is between 1 and 2. So visually that's everything between 1 and 2 with the open circles, so with the two endpoints excluded. Then we have 1, 2 with brackets, which implies both 1 and 2 are included. So this becomes x is in between 1 and 2 with the equal signs. So visually you would have closed circles for 1 and 2. And then we could also have a combination. So for example, you could have a parentheses and a bracket. That implies 1 is excluded and 2 is included. So you'd have an open circle and then a closed circle. This instead is not an interval. When you use these types of brackets, you have that x can only be 1 or it can be 2. So it's only those two possibilities. And so because there are gaps, even though it's a one variable set, it's not going to be called an interval. So again, an interval is specifically a set in R that has no gaps. And then two more things related to intersection and union. Here we have the x does not belong to the intersection. So visually, if the intersection is the middle part, then we will be taking everything outside. So this is the intersection, and what we're looking for is actually everything outside. This is equivalent to saying that x does not belong to A, or x does not belong to B. And notice how I'm saying or, even though intersection means and. Because by splitting it up like this, by looking at A and B individually, it's going to change the way that we can represent this information. So if you look at the diagram, it actually helps to make sense of it. Because if we suppose for a second that we had an and here, if x does not belong to A and does not belong to B, that would mean that it would be actually everything over here, which is not what we want. We do want to consider this portion and this portion as well. So by saying instead or versus and, that's implying that x does not belong to A, so either it's not in A or it's not in B, not necessarily neither of the two. So basically it can be A but not in B, which should be this portion. Or it could also be in B but not in A. It doesn't necessarily have to be outside A and also outside B. And the opposite of this, or not exactly the opposite, but is a similar situation almost in reverse, is when x does not belong to the union instead. So the union would be everything here. So if x doesn't belong to it, it's everything that I have shaded in green. And then it's the same idea that even though union means or, when you rewrite it like this, you have to use and. So when we say that x does not belong to the union, it's like saying that x does not belong to A, so it's outside A, and it's also outside B. So I know it's a little bit counterintuitive, but this is something that is relevant for a proof, so it is going to come up later. The most typical notation that you can use for any definition is this one. We're saying that we have a function such that the domain A maps to the codomain B. So this can be used to generalize all functions of any type, regardless of how many variables we have for the domain and codomain. But the most typical one is this one, where we have a domain that is a subset of R1. So this is implying it's a one variable function, and the codomain is all of R. Notice how it's also R1. To clarify, we don't write the 1 normally, but it's implied unless we write otherwise. So this just implies you have a domain which is a one variable domain. It might be all of R or it might be a portion of R. And the codomain, which we're going to talk about more in a minute, represents all of the possible values for the outputs. So for one variable function, that would represent the possible y values. It's not the same as the range, so it might by chance end up being the same, but generally it's two different things. And if specifically we have a function that maps R to R, then this is implying that the domain is not just a subset of R, it's all of R. So this can be relevant. So when you see this kind of notation in exercises, you want to make sure that you check whether it gives you any specific information about the domain, whether it's a subset of R, which is not really telling you anything except that it's one variable domain, or whether it's specifically all of R. This can affect how the function is going to look graphically and different possible properties about it later on. If we have that the domain is a subset of R2 or R squared, then it's saying that we have a two variable function. Notice how the domain is still R, it's not R2, because with two variable functions, we're going to still have one output. So it is normal for this to not be R2. And so a two variable function could be, for example, this one below, where we have f of xy equals x squared plus y squared. So for this one, if we put in a random combination of x and y, let's say we put in 1, 2, if we do the calculation, 1 squared plus 2 squared is going to give you 5, it's going to give you a single output. So we put in two inputs and we end up getting one output. So to see how the codomain is relevant, usually the codomain is going to be R, in which case you can essentially disregard it because it's the classic situation, which is telling you that you can consider all real numbers. But if instead you have specifically that the codomain is 0 to infinity, That's telling you that no matter what the function is, you're only allowed to consider the positive part of the y-axis. So this could also come up in micro, for example, because with micro you're going to have utility functions. A utility function measures the level of satisfaction that you have with the product. So for example, if x is the quantity and u of x is the utility, both quantity and utility are generally going to be assumed to be positive. So they might tell you that your domain is positive real numbers and your codomain also. So this means that you can't consider negative quantities and you also can't consider negative utilities. So they might use this. And so this portion in particular is a codomain, which is going to restrict the y's. So if we're looking at the function x, generally the function x would just be the classic straight line through the origin. But if specifically we're told that we're only allowed to consider positive y's, we're essentially going to cut off the bottom part, the part that would have negative y's. And this in turn is also going to have to restrict the domain. So in this case, it does have an effect on the graph, so this is why it's important to look at whether you have any restrictions for the codomain, although they are very unlikely. And in this case, the range, which is the actual y values the function can take, would end up coinciding with the codomain. So the range, which we can call FA, or also IMF, so you can also write it like this, is going to be all the positive real numbers, which in this case is the same as the codomain. Later you'll see that if the function has a range that matches the codomain, so range equals codomain like it does in this case, then we can say the function is surjective. Otherwise, if the range is a strict subset of the codomain, so it's not equal to it, it's just a small part of it, then the function is not surjective. So surjective just means that the function takes all the values in the codomain. And then here we have a different example. So now the codomain is everything from -1 to infinity. And we have the function x squared, which the general graph would be this one. And now according to the codomain, we can only consider the y values that are bigger or equal to -1. In this case, by nature, the y values are already bigger or equal to -1. Specifically, they're bigger or equal to 0. So we don't have to remove any part of the graph. So the graph is going to stay the way it is. But the range is the actual y values the function is going to take. And as we said, in this case, it's going to be all the real numbers that are positive. So notice how in this case, the range is a strict subset of the codomain. It's not equal to it like it was before. So in this case, the function would not be surjective.